Well, good morning. Thank you, Franz. Thank you, Karl Herbert, for the introduction. I'm really glad to be here, home in Kaiserslautern. This is a rare possibility to have conferences here because of the limited capacity. I take the chance to also talk a bit about DFKI. I'm not sure who knows about DFKI. Who knows MIT? Okay. Yeah, so you should know DFKI is the largest AI institute in the world. It has its headquarters in Kaiserslautern. It's a non-profit research company guided or directed by university professors and has about 1,280 people working at it. We have about 350 projects. And as a company, we have owners, so companies who own shares. These are, of course, the common German suspects like SAP, or the OEM from the car manufacturers, and Munich Re, and who else? Sartorius, Bilfinger, many companies, but also international ones like Google, Microsoft, Intel, Nvidia, and Ricoh, even Japanese ones. So 33 shareholders. And we are offering our solution and technology know-how to not only the shareholders, but to the entire market, which means that we are directly there, where Franz mentioned, at the interface between the blue sky research at the universities, we are all professors at universities, and the applications. And as I mentioned, we are doing lots of projects. They are not all in life science, of course, only some of them address this topic. Many of them are in energy. We just 2 weeks ago, I signed a big contract with ESA about Earth observation and sustainable goals. So many different topics which form a huge amount of problems for decades to be solved. And that's the really challenging and the really great thing to work with young people who are creative. And I'm delighted to give you some insights into our hotspots these days. And my title today is about a specific perspective on artificial intelligence, namely on this intelligence amplification. There was also already in the late 50s, early 60s, a big discussion about what is AI. And there are many people who discussed about, is AI something which is addressing to build a homunculus? Or is it rather a tool, an engineering tool which takes over step by step also cognitive tasks without the holistic view to the world, without being able to reflect, but in some sense could act as an amplifier to help us solving problems. And this is something which is these days, again, quite popular. Also, there are well-known colleagues like Kurzweil, who promoted this downloading of your consciousness and uploading to an avatar. He failed again in this announcement. We are still on the way, of course, to develop this amazing technology. And in the next years, we will profit from this technology in lots of domains. And I'm addressing today the life science domain. So, and hopefully this works. Yeah, coming to AI, it's not new technology. As you know, we had different waves. And when DFKI was founded in the 80s, there was already the second wave where the first expert systems were the market. And all the nations, the big nations, came up with, well, we should found a own national research center. And there was a competition in Germany and among Hamburg, Munich, and Karlsruhe, Ulm, Aachen. But finally, we made it, and it was founded here. I was not a professor, of course. I was just in my PhD phase, and I worked in the US. But fortunately, my first advisor became the first director of DFKI, and he called me and told me something going on here. And I said, well, Palatinate, Kaiserslautern, but you can see I'm still here. This is because we have this environment which provides really fantastic research options. And now we are in the third wave. DFKI was sometimes called the last dinosaur, but we grew and were very successful. Can mention some really hot spots of our development, but this is another story. And these days, we have three major dimensions which are quite important for AI. This is data. Yeah. This is coming, of course, through the internet, through the sensors, and the combination in the Internet of Things, which is an important aspect here. This is second, also the evolution in this part of deep learning, that from 2012, maybe this was the year where it was the realm of AI, pushes all the technology and the research in this domain, and finally also the compute power. So when we started, I met Norbert Kuhn. He was one of the companions there. Norbert, where are you? Here. So he was one of the early companions at DFKI, but you also may remember that we hunted for data. Yeah, how can we get the data to apply AI? And nowadays we are in this fortunate situation that if you look around, we are producing data every day that is, of course, sometimes double, but it's coming through all the sensors we have in cars, at street lights, in your mobile devices, but also the sensors in the internet which are able to track what you're doing, so many sensors. And they cause that nowadays we're producing data that is, if you put it on DVD, we can build a stack that is about 20 and more times the distance between Earth and Moon. And this makes obvious how much data it is. And then therefore it reveals a lot of options, although you will see that we are not yet data ready in many domains, also in life science. Still lots of things to do. So if you look to the development in the deep learning field, I also think this semantic network are still okay, and they are also in some domains quite successful. If you look at the so-called enterprise knowledge graphs, even used in the new Google search, but this is also another story. We can see that there are lots of different dimensions. So we have an entire landscape of aspects, namely you have different inputs which could be processed, data from images, video, text, you have remote sensing, knowledge graphs, sensor data of typical aspects, time series, you have network types, different aspects, well-known autoencoders, convolution networks, recurrent networks, combinations of them, and also different tasks to be solved, from segmentation to classification to tracking to translation, many aspects. And you have also architectures which are state-of-the-art, which are used in a lot of domains, and components which are contributing to design architectures in a certain way. And for students and also for researchers, there are at the same time lots of tools. And it's like a forest where you're looking for the tree. Yeah, and therefore, if you are a beginner, it's quite important also to see that there's the option to consider these dimensions as facets where you can browse through, where you want to solve specific tasks or you want to apply certain architectures. You would see what is a tool offering, and therefore you get an orientation in this forest, what's best fitting to it. And this is a tool we are also offering our students and researchers when they start to get a certain orientation, what could be first applied for solving tasks. You can also combine the facets and narrow down this kind of search more and more. However, if you look into the last years, you can also see that it's not only an evolution in accuracy, in performance of deep neural network. You can also see that these networks get, if you take AlexNet from 2012, the original one, and would go in the future, this is just a snapshot which is published in 2018, I guess, so far. And you can see that, however, the number of operations are growing, and therefore at the end you need more power, computing power, because you have a training phase, and this should be organized in a certain way, and maybe you want to verify a certain hypothesis. So it's quite important to see that there is also a big demand, and this is a really big problem in Germany, that we are not ready yet to compete with other countries. We have some small islands, DFKI is one, fortunately, yeah, where we have enough power. And the idea you can see here, if you have the power to verify hypotheses. If you go 6 years back, almost 6 years now, we had a big training set in use, about 100 million labeled images and videos. And we started to train a network at the time on the technology available. We needed 6 days for the training. But companies like, for example, NVIDIA, whom we have a close collaboration, there's a founder of NVIDIA, the CEO, Jensen Huang. He thought about, well, using these graphical processing units basically designed for real-time visualization in games might be also usable for special or promoting special AI architectures. So invested in these architectures and came up with, for example, this DGXs generation, the 1 and the 2. And if you look at the DGX2, which is not the recent one is the one, the AI100 shown here, we saved a lot of time. Just 18 minutes were needed for the training, which allows us, well, to verify lots of different things at the same time. It's much more fun for the PhD students finally to work, you can imagine. And this is also something which is going on, of course, with the problem that we are requiring power and generating a lot of heat. But anyway, these are the 3 driving forces in artificial intelligence, and as I mentioned, fortunately in DFKI we right now have about 50 petaflops as the theoretical options for computing. So AI is a fantastic tool which is used in different domains and reaches recognition results which are close to humans or even better than humans, and you might already know about DeepL or DeepL, coming from a company in Köln or Bonn. They did translation services for the EU for decades, so they knew very well how a document in German should look in French, yeah, or in Portuguese or Italian. So they just, instead of establishing grammars, which you remember in school were quite important to learn a language, they just feed it a deep network or combinations of them in order to make the translation possible. And so you can see this, I just typed in this text, it's quite impressive. Also, if you used it, you can see you can translate entire proposals from German to English if it's needed, or reports. But you can also see I used this text to demonstrate that the system has no idea about language. And it has no idea about the statements which are written, whether they affect or even, well, have some negative impact on the reader. Yeah. So there's no reflection what consequences this causes for the society or the humanity. So, but it's an excellent translation system. So it's a tool. Artificial intelligence amplification. So, but I also try to think about what that means, that if we have such a tool reducing complexity in a certain way and helping us to be faster, better in a certain way, to look at the life science domain. So if you look at life science, there are many options nowadays to use data. Data is manifold, and this data is usually considered as the input to solve problems. This data is coming from experiments. So if you look at cell lines, animal models, you have also histologies, other things. You have the biological data sources, the genome data, some epigenome or microbiome data. You have the clinical data, the family, the vital aspects, the medications, etc., but also the environment, which has influence in a certain way, and the variables. Of course, continuously recording the data while you are doing something. And this data is usually used as the input for one of the traditional research fields in AI, namely feature engineering. That you, as an expert in medicine or in biology, you are able to take the data out, try to normalize it in a certain way in the format and cleaning it and then scaling it, and then use it in order to select the appropriate machine learning algorithm. And there are many of them to establish a certain model, which could then be mapped to a new observation and be evaluated, and you get some feedback. This is the typical way, but since we have these options for deep learning, we can also build on end-to-end solutions. So where we don't need the feature engineering anymore, sorry, what happens? Oh, there's something missing. So we don't need this anymore. Just we have one part, end-to-end learning for a certain model. And these models are at the end powerful, and they could even used for transfer learning. I'll show you also examples how we can apply this. So there are many options specifically for imaging problems, where you have here, for example, in radiology, options to find the tumors in a certain way with a high accuracy, where you have a combination. Here the feature engineering in this paper is explicitly done before. It's not part of the deep learning, which is also a very common approach. But there are also other solutions in tomography, for example, which provide exemplary, here in this case, nice results. I would address another problem here on which we are working. This is in ophthalmology, where you have well, images again from the eye, inside the eye, which is illuminated, and you can see a lot of this vascular system here. And one of the very common diseases is glaucoma. And you can use typical structural evidences to measure glaucoma, also the vascular changes of indications, which are then employed by the experts in order to find out which state of glaucoma you are in. Are you healthy, or at the end, have you already a severe status? And in between, there are different aspects, and you can, if you are experienced enough, identify these states and to make your diagnosis at the end. So here again, it's not needed if you use a appropriate deep learning architecture to train everything, but rather to look at all the features explicitly, but to train the system by appropriate data, labeled data about the different states, and then get insights. However, one of the major aspects here is to first have methods to identify the optical disc, because this is the main aspect of observation. So you need a two-step procedure, where the first end you have the option to take images, retinal fundal images, and then develop a kind of approach, here also a kind of feature extractor, to have a box classifier at the end, to have this region of interest as the optical disc, which could then serve as a means for another network, which applies then a classification task very accurately. So we used, in our case, about 6 different data sets, which are public, but also very closely worked with ophthalmologists who provided us an additional data. And you can see 4 of them had a 100% accuracy. So these are state-of-the-art data sets, and the other one is close to 100%. So it's working quite well, and you can also apply the same approach for the detection of diabetic retinopathy. And so you can read the papers. If I will also hand over my presentation, so if you are interested in that, you can have a look in the papers. Another application is microscopy. We can use the images of some investigations here. You can see these are images taken every 5 minutes. So a sequence of images. It's not a continuous tracking, but it's an attempt to track the cells. But if you want to really somehow automatically identify biological phenomena, you have to work on these images because you can see there is a lack in contrast, yeah, and there are some challenges which are given. Specifically, the segmentation of cells, individual cells, is of high importance because this is the basis then to proceed to study about the cell behavior, about the lineage, about tumor growth, etc., etc. But if you look into the literature and research, up to now there was no single deep learning approach which is able to really employ a big data set up to now, as in many other problems. So we worked on that together with colleagues from Sartorius to build an entire pipeline for detection and segmentation of cells, which is label-free segmentation approach. And this allows us to, at the end, use this big set of 1.6 million cells, as I mentioned, label-free, to build a very accurate cell detection and segmentation, which then gives us the basis to investigate many different aspects. It's all paper in Nature, methods where you can get more information about it. But what you could do at the end is you can really build a cell tracking algorithm where you could just enumerate the various cells. You can see the different divisions of the cells and track them in a high accurate way. And moreover, you can also verify certain phenomena. For example, we verified very easily with this method detection, which is made by a colleague of us in biology, that if you have aneuploid cells, so which behave strange if they split, so they have a chromosome, they have about 60 to 90 chromosomes at the end, and this causes cancer. So we could verify that after 125 generations, yeah, such tumor cells behave different. So there's a certain anomaly just by tracking such microscopic images. So finally, I'd like to go to Demathology, an important and one of the hot spots in medicine. And I first want to address a paper from colleagues from Stanford, also in Nature, that they could very early already show that a deep learning system is able to reach the same quality as an expert in the field, just by getting a training set to distinguish finally between carcinoma, melanoma, or NAVI, whatever. So, however, the problem here, and Franz mentioned it already, it's a black box. And this black box aspect is inherent for many applications, for automatic driving. For other domains, I have to stay in front of the camera, sorry. Systems behave because we use a training set, and we don't know exactly, is it balanced, does it have a bias? Yeah, because we are subjects, and we cannot overlook all the aspects in the data itself. So specifically, this explainability plays an important role, and the hardcore case is the deep network. So we know feeding it, at the end something's coming out. And so in our case here, we are not only interested in reaching a high classification rate, but rather producing a certain explanation as an expert could do so. So we started to justify or develop methods to justify the decision of deep neural networks. So if you look into the domain of skin lesions, you can detect or recognize that even the doctors whom you visit have problems in really saying it's a melanoma, so it's malignant or not. because you can see from the images it's not that easy, because images are all different. And at the end, there's also no real gold standard for the diagnosis. And this is a lack in many of the life science domains, that these data sets are not yet available, because all the data is patient-oriented on one hand side. It's very individual. Our body is complex in all the interactions and relations, what's going on. And however, this is a problem as in many domains. So if you look for the skin lesions, you can detect that there are lots of different aspects here. 4 main categories could be recognized. This is that there are certain recrescent structures inside the different lesions. You have radial extensions in a certain way. You have irregular or regular distributions. You also have complex lesions which are composed of different colorings, etc. And you have structural networks with some pigmentation. Some of them is typical or some of them is atypical. And based on these different categories, you could also see that there are concepts, visual concepts, which are part of this and give maybe an implicit orientation to every expert, how to diagnose finally such a lesion or not. So in practice, you can check plausibilities, if you are using certain checklists which are adapted to these concepts, because the checklists help you to make the concepts explicit, that you have a special perspective on each lesion. For example, to investigate aspects like the symmetry or asymmetry, how it is blurred or sharp at the boundary, what colors are there, how many are there, what is the diameter of the lesion, and also to see over time how it is evolving. And based on that, the doctors usually use a couple of techniques to do so. One of them is the 7-point checklist, the ABCDE rule, where you are following a certain scheme, where you have this dermatoscopic criteria here, and a kind of option with a slider to rank it. There are the concepts I already addressed in a certain way, that you could see how the pigment network looks like. Is it there or is it not there? The same holds for all the other concepts, the streaks, the recurrent structures, the symmetry, asymmetry, etc., etc. So it's making implicit knowledge of an expert explicit by just using this. And this is also something which you can apply also for AI and AMI methods, namely that you can look into these images more deeply. So we applied here a new approach, which is composed of various steps, and it's also employing a specific technique which is built on so-called concept activation vectors, first introduced also in 2018 by colleagues from Stanford, but they applied it in a different way. So first of all, there is a need to collect data from experts. So we asked experts to annotate the data in a certain way, whether some of the concepts are present or not. In the second step, we used already pre-trained high-performance CNN, where we have this end-to-end feature learning, and it's not needed to have an explicit domain. But, yes, so you can have some image inputs, and the network is pre-trained already, and you have the feature maps inside, and at the end the system tells you it's probably a zebra and not a wolf and nothing else. So it gives you a certain probability back. This is the initial state, and this network was not explicitly trained to lesions in this status here. So in the next step we use additional data, so look for data which allows you to get similar concepts we might address in our dermoscopy domain, and which, however, should be visual understandable. And then we are applying these concept activation vectors, the test from them, to map the concepts of a human physician with the representation learned through the skin lesion classifier. meaning that we used a big data set about textile. So we had different textile motifs and patterns inside, and we used the pre-trained convolution network, which is trained on a completely different data set. And at the end, well, the system said, well, this is striped, labeled as striped, and the system, however, comes up with a zebra. Yeah, this is nothing surprising us, but this is the case. So now we are making use of something which is typical for neural networks, namely that we are considering the hierarchical way they learn the features. Meaning that close to the input, you have basic features like corners or edges which are learned, and the closer you come to the output, these features are composed and finally are close to your own classification tasks, to complex features. So what we are doing here is we are, oh sorry, now I have to go back because somehow the arrangement is, so we are tapping the network at the various layers to get the features out of them to train individual concept classifiers, independent of what the system does usually. And based on that, so we take these as the classifier, and the classifier has this kind of hyperspace where we have the separation of the concept and the non-concept features at the end, and we are able then to get a certain representation of the various concepts in the skin lesion images. So at the end, after learning the concept, we do quantification, determines the contribution each concept makes to prediction for an individual target class at the end. And therefore, we could employ this to classification, but also to explanation. Meaning that if we have such a problem, and the problem is solved via the different classes, as mentioned here, we can apply this and get then by retraining the pre-trained network by lesion images, we get classification for a benign or a melanoma or basaliom, whatever is inside. But in addition to that, the system is able to employ these concept classifiers to tell us about why the classification is done like this. So for example, it gives us an explanation that it detected specific features inside, like asymmetry here, or the irregular points, but also some atypical pigment structures inside. And this entire system, Adriano is also here, Adriano Luccieri, who is the first author, and he's also presenting the work outside at a poster. So if you want to know details, please ask him. He's sitting here also in the audience. And he is also integrating the entire findings into an interface. You can find the interface here at the URI. And this interface visualizes the entire lesions themselves and gives you an insight into the classification results based on the various concepts which are present. It gives you metadata about the patient, a kind of prediction of the classes, and you can see already here first attempts to transform the result into a textual explanation. The same could be also viewed from a different dimension, that you have a transparency slider here, that you can see whether certain concepts are present or absent via these heat maps, and also have insights in the entire data set for the experts to see how the data is composed and see the data distribution at the end. We can also further develop this, and we did this, show you another dimension, not only for images, but you also have other data which are important, life science, namely time series. And we not yet applied it to life sciences, but we used other domains where we have 200 different time series at the same time. from big engines. And the task here is to find correlations and at the end to detect anomalies. But in medicine, there are very similar problems. So if you have such an anomaly, we are now also able to transform them or to give an explanation why an anomaly is caused, either by a short text, which is automatically generated by the system, or even by a longer explanation. So this is based on text patterns, which are complemented by the input data and by the result data to give these explanations. There's also a paper, you can see it here, if you are interested to read more. So at the end, my takeaway is AI is a fantastic technology for humans, and the biggest potential here is in this intelligence amplification, because it takes complexity away for which our brain is not made, and specifically there detects the patterns which are relevant to be better or faster. Thank you very much.